In this video, we're going to discuss two more examples. Let's discuss the second example, a diagram of a heat sink that consists of 9 thin fins is used to remove heat from a surface whose temperature is equal to 60 degrees Celsius. So the temperature at the base of this fin is 60 degrees Celsius. The temperature of the ambient air is 20 degrees Celsius with convection heat transfer coefficient H is equal to 15 watt per meter square Kelvin. The thermal conductivity metric of the material used is 175 watt per meter Kelvin. The fin is 60 mm long, 40 mm wide, and 1 mm thick. So therefore, this will be our thickness, and this will be the length of the fin, equal to 60. The sides and the tip of the fin are sufficiently thin so that the heat transfer from the tip and sides can be neglected. Determine the temperature distribution along the fin in x direction using 3 equally spaced elements, meaning that the length of the element for all the elements should be the same, and the total heat loss for an array of 9 fins. Determine the temperature at point P as shown in this figure. Let's solve this problem. Let's illustrate this problem with only one thin fin as shown, where the fin base is located at the bottom of this fin with temperature 60 degrees Celsius. We are required to solve this problem by using 3 equally spaced elements. So for the first step, let's draw the free body diagram to model the fin using 3 1D elements. As we divide or discretize the fin with equal length, therefore each of the element will have the length 20 mm. And in previous video, we have discussed that for thin fin problem, in general, the temperature at node 1 is always assumed to be the same as the temperature at the fin base. Therefore, in this case, T1 is equal to Tb. Hence, there are 3 degrees of freedom in this problem. Next, we have to determine the element conductivity matrix for each element. As the fin is made from the same material and the length is also the same for all elements, therefore the element conductivity matrix will be the same for all elements as shown. Once we have solved the element conductivity matrix for all elements, then we can assemble them in order to form the global element conductivity matrix for this problem, as shown in this slide. In step number 4, we have to determine the element convection heat transfer matrix for each element. Similarly, as this fin has been exposed to the same convection process and having the same length and thickness, therefore, the element heat transfer matrix for all elements will be the same as shown. The next step, we just need to assemble them to form the global convection heat transfer matrix. The next parameter that we have to determine is the element heat rate vector, and we have to determine first for each element. Similarly, as the fin is exposed to the same convection process and having the same length and thickness, therefore, the element heat rate vector will be the same for all elements, as shown here. Then, we just need to assemble them in order to obtain the global heat rate vector. Once we have determined all the required matrices as shown, then we can write the global system of linear equation using this formula. To simplify our global system of linear equation, it is better to obtain the summation of K matrix plus the H matrix. We just need to add these two matrices according to their position. For example, K11 plus H11, K12 plus with H12, K21 plus with H21, K22 plus with H22, and so on for other values. If we do for all values, then we will obtain the summation of K plus H matrix as shown in this matrix. Next, we just need to add the unknown temperatures and the global heat rate vector on the right side. However, at this stage, we cannot solve this system linear equation. We have to impose the boundary condition first, then only we can determine the unknown temperatures. Now, let's impose the thermal boundary conditions. As discussed in the previous video, for thin film problem, we just need to focus only one type of boundary condition, which is the specified temperature. For the specified heat flux, which is Q equal to 0, we can neglect this boundary condition as it won't change or give any difference to our global system linear equation. So now, let's focus on the specified temperature. In this case, T1 is specified, which is equal to 60 degrees Celsius or 333 Kelvin. Therefore, we can eliminate the row and column for T1. And remember to check column 1 at the other rows. For example, in this case, we can see that the value in column 1 at row 2 is non-zero. If this value multiply with 333, it will give a constant value. And we cannot neglect this value. We have to bring this value to the right side. When we bring to the right side, this value will be positive, as shown here. Then we just need to focus those values in this green box. Then we will obtain our modified system linear equation, and then we just need to use the calculator to calculate the unknown nodal temperatures as shown in this slide. Next, let's compute the heat loss from each element. As we have determined the unknown nodal temperature in the previous slide, we will use this information to obtain the heat loss from each element by using this equation. So in this case, the H value is constant, which is 15 for all elements, and the T average for H1 is taken from element 1, as element 1 is between T1 and T2. The ambient temperature is constant for all elements, and then the surface area of element 1 that exposed to the convection process. Remember to consider only the length of the element 1, which is in this case is equal to 20 millimeter. And do not forget to multiply the area with 2 to consider the top and bottom surfaces of element that expose to the same convection process. For heat loss in element 2, the T average is taken from element 2, taking into account the average between T2 and T3. And the rest value are similar to element 1. And the last heat loss from element 3, the T average is taken from element 3, which is the average between T3 and T4. The T ambient and the surface area exposed to the convection process will be the same with other elements. So once we have determined the heat loss from each element, then we can compute the total heat loss from all elements. First, we just need to obtain the total heat loss for one fin, and then we just need to multiply with the number of fins used in the system, which is 9. And then we will obtain the total heat loss for this system. Now, I would like to discuss additional analysis. For example, let's determine the temperature at point P, which is located 30 mm from the fin base, or it is located at the middle of this fin. In free body diagram, we can see that point P is located in element 2, which is between T2 and T3. So let's take out this element 2, and we can see the detail of this point. So in order to determine this temperature at point P, first we have to determine the value X. So as we know that the distance between node 2 and node 1 is 20 mm, and we can determine the distance between node 2 and point P, which is 10 mm. So X is equal to 10 mm, and the length of element 2 is 20 mm. And T2 and T3 is already defined in the previous solution. Therefore, by using all this information and substitute into this temperature function that we derived in the previous video, we can obtain the temperature at point P, where X is equal to 10 mm, LE is 20 mm, and T1 and T2 in this equation will be T2 and T3, as we are trying to solve this point P at element 2, which involve T2 and T3. So by replacing T2 and T3 into this equation with X and L, we can determine the temperature at point P, as shown here. Besides that, if we notice, this point P is located in the middle of element 2. Therefore, the temperature at point P can also simply solve by taking the average temperature between node 2 and node 3. This is only true if the point that we would like to determine the temperature is located at the middle of the element. Let's have a look on the third example, which is a very interesting example. In this problem, a rectangular fin is used to remove heat from a surface whose temperature is 100 degrees Celsius. the temperature of the ambient air is 30 degrees Celsius with convection heat transfer coefficient of 12 watt per meter square Kelvin. The thermal conductivity of the material used is 350 watt per meter Kelvin. The fin is 120 mm long, 100 mm wide, and 5 mm thick as shown in the figure below. Here is the interesting part. Due to the safety reason, 1/3 of its length is insulated as shown in the figure. It is assumed that no heat flows at the side of the fin and at the tip. Determine the temperature distribution along the fin using 3 equally spaced elements. To solve this problem, first we have to draw the free body diagram as shown. We discretize this problem into 3 equally spaced elements. Therefore, each element is having the length 40 mm. If you can notice, for element 1, I put in the green color. This is to differentiate with other elements that element 1 is being insulated. Therefore, element 1 won't be exposed to the convection process. However, the conduction or conductivity still occur in element 1, as this fin is a continuous body from the fin base until the tip of the structure. So the conduction is occur within the fin. It's not separated. Like in convection, the top surface and the bottom surface of element 1 is being insulated. That is why for element 1, it does not expose to the convection process. Okay, next, the boundary condition, as usual, we assume T1 is equal to TB. Therefore, we have 3 unknown degree of freedom. Next step is to determine the element conductivity metric for each element. Like in the previous example, as the fin is made from the homogeneous material having the same length, therefore the conductivity metric for all elements will be the same as shown. Next is to assemble these element conductivity matrices to form the global conductivity metric in the usual manner. The next step is to determine the element convection heat transfer matrix for each element. Remember, as I mentioned in the previous slide, element 1 does not expose to the convection process. Therefore, for element 1, the convection heat transfer matrix will be 0. But for element 2 and element 3, they are exposed to the convection process and exposed to the same convection process having the same length and thickness. Therefore, H2 and H3 is equal as shown. Next, we just need to assemble these 3 heat transfer matrix to form the global convection heat transfer matrix as shown. So we can see that in the element 1, for column and row T1, the value is 0. As element 1 is having 0 H matrix. Next is to determine the element heat rate vector for each element. Similarly, for element 1, since it does not expose to the convection process, therefore the heat rate vector for element 1 will be 0 as shown. For element 2 and element 3, the heat rate vector will be the same, as they are exposed to the same convection process and having the same length and thickness. The next step is to assemble this heat rate vector to form the global heat rate vector matrix as shown. Similarly, for row T1, we have 0 value, as the heat rate vector for the first element is 0. Similar in the previous example, once we have determined all the required matrices, then we can write the global system of linear equation using K plus H times T equal to R matrix. And for K plus H, we just add these two matrices in the usual manner as shown here. And after this, we have to impose the boundary condition, then only we can solve the unknown nodal temperature. So in this case, T1 is known, which is equal to 373 Kelvin. So we can eliminate row 1 and column 1 as shown. And then similarly, we have to check the column 1 for the other row that's still active. For example, in this case, it's clearly shown that column 1 in row 2 is having non-zero value. And when we multiply this value with T1, which is 373, it will give a constant value, and we have to bring this value to the right side. And when we bring it to the right side, the value will be positive, as shown here. And then we just consider those values in the green box. So once we have modified our system linear equation, finally we can solve this problem by using calculator to calculate the unknown nodal temperature as shown in this slide.